Let's begin. Welcome again. So now I'm going to be one of those people who post like these memes on every lecture, like there's a life lesson. But I think they're valuable. I don't know, like there's, privacy is a big deal in this day and age where like you get emails or texts from people, like, who are you? How did you get my name and number? And like you go and search for yourself. There's like 7,000 websites out there that dig your information. Half of my life, because I grew up outside the US, doesn't exist, which is nice. Like, if you look me up, I exist in the US suddenly I came online at the age of like 25. I'm 27 now, so that was 2 years. I was like, I came online at the age of 25. He has no record before 25. Maybe he came from Krypton or something. So that's good, but and privacy in your life and with friends. And I know sometimes like you want to share vulnerable information, like maybe you're going through a rough time or a medical condition or something in the family. Also choose the people you share with wisely, because the line of people who want to critique and gossip is 10 times longer than the line of people who want to help and sympathize with you and actually help you out. Anyway, so just a little comment. Let's go back to our heat transfer problem that we solved last time, and we left off like right at the apogee, at the best part where we actually got to a solution. Just to remind you of what was going on, we had a material that's heat that's at a fixed temperature on both sides, and there's some source of heating in the middle or somewhere here or there that's adding or subtracting heat from the material. And we said that the equation that governs the heat transfer, which can be described in terms of temperature in this material, is given by this ordinary differential equation. I said don't worry about how we got this, and even the equations that we are solving at every grid point as we describe the process. I will give you those, but this was a great example for how one could obtain large systems of equations. So I want to get back to our Jupyter notebooks, which I conveniently have right over here. So just go back and make sure you are in sync with what I got here and consistent. Make sure if you run this again, it runs. We had the source routine here described, the plot. Some of you let me know that sometimes the plot doesn't show when you just do this. You have to do plt.show. That's totally legal. Okay. Again, I'm not gonna debug your code or judge you on the code you're writing. Obviously, I prefer cleaner and efficient code, but that's not my primary concern here. So if you had to put plt.show for the plot to show, that's great. You figured it out. Good for you. And and if you want to use GPT, for example, to show you a few tricks to make the labels and the fonts look better, all the power to you, right? So it's to me, GPT is an augmentation tool, or any of these AIs, just like you would Google, how to make my labels on a plot, etc. And you steal the code, copy the code, and adopt it. That's great, and hopefully you learn something along the way. The meat of our work was in this section here, where we specified the temperature on the left and the temperature on the right. And I called those T0 and TR. I could have called them T0, TL, or TL and TR. It's just weird. T at L and T at 0. Anyway, so we just call them T0 and TR. Thermal conductivity, we set K at 300. And remember now, because we're going to do some critical thinking in a minute, that K was called the the thermal conductivity, or the heat conduction coefficient. That's the ability of a material to pass on heat from one molecule to another, to pass on that vibration from one molecule to another. On average, from a macroscopic perspective. So there's no K at the microscopic level. K is a macroscopic property of the material. So the larger the K, the faster that the heat is going to go through the material. So the heat that's coming from the source or the boundaries is just going to propagate much faster and equalize the heat distribution everywhere. The smaller the K, the more resistive the material is going to be to passing on heat. And we built these diagonals, main diagonal, upper diagonal, lower diagonal. We blended them together in a matrix using the numpy.diag routine. Now, this matrix is a dense matrix. What I mean by that, it's in memory, in the computer, it's storing all the values in the matrix, the zeros and the non-zeros, okay? It's a full dense matrix. Although the zeros are just zeros, we know they don't mean, they mean a lot for the system of equations, but in terms of storage, you know, what, do we have to store them? We're going to talk about this after we finish with this example. But know that this function gives you a full and dense matrix, so it stores everything, every number in the matrix. Then we defined our right-hand side vector. So I hope you're consistent. All the code you guys in the back can see. Okay. And then we solve the system. We build the coefficient matrix. We have the right-hand side, numpy.nin algebra.solve, a comma b. So we gave it the system, the coefficient matrix, and the right-hand side. And what did it return? It returned a temperature, an array of temperature values. What are those temperature values? They are the values that correspond to every point in our grid or our discretization. Okay, so when we go back here, what the system returns to us, it returns T0, T1, T2, T3, T4, all the way to T100 or T1000 or T5000, however many points we put. Okay. Now, the way I set this up, if you remember, although I knew T0 and I knew T at the end of the domain, I still put them in the system of equations so that they are part of my final solution. All right, so when we did this, we had temperature on the left 500, temperature on the right 300. And let's clean this up a little bit. So I'm going to put a grid so I can see what's going on here. plt.grid. Have a nice grid. Okay. The first thing you want to check is, did you catch the boundary? Did you capture the boundary conditions in your solution? Yes. T at x equals 0, I have 500. And at x equal 1, or L, I have 200, which is the value which are the values that I put up there. Good. So at least my system is satisfying those boundary conditions. Okay. Then I had my source term, or the heating thing that is heating the rod. It was right in the middle. So I'm going to expect either a peak or a change in the temperature profile right at that point. And indeed, exactly in the middle, where I have that heating, I am breaking that temperature distribution. So it kind of looked like it was going this way, and then suddenly it went down this way, right? Or as if it was going to be up this way, and then it went down this way. So this heating source is doing something. Okay. So now we can have some more fun with this. So how about we put the temperature on the right to 450, let's say. Okay, we're going to have something like this. Well, yeah, that kind of makes sense. I still have 500 on the left, 450 over here, and the heating source is causing a peak in the temperature because I'm heating the material, I'm adding heat. And I can make the two temperatures equal, 500 and 500. Then I should expect a peak, and then it's going to come down because that heat is just going to be distributed across. Okay, so let's play around a little bit with the source to verify this, that I'm getting this right. I'm going to put A to be the location of the heat at 1/3 of the rod. So I moved it to about 1/3, 0.333. And then I can execute this again and plot it. And indeed, the heating just kind of moved away from 0.5. It's close to 0.33, but that's kind of what I expected to peak. So it looks like my system is doing the right thing. Right? It's doing the right thing. It's behaving the same way. I still don't know if that's the exact answer because I don't have an analytical solution, right? But all of these things gave me confidence. And especially when you are going to be in a situation where you actually cannot verify your solution, you can only compare with experiments or just trust that your system has worked on the simplified cases where, okay, we satisfied boundary conditions. This looks like it's behaving correctly. Okay, this looks good. I have some confidence in this. We're not going to talk too much about how you can further make sure that these solutions are correct. There are techniques where you can refine or use a higher order approximation and compare it with the lower order approximation like we showed for the derivative. We're not going to worry about that now. But these are like quick sanity checks. OK. Next, I want to play around with K. And I want to ask the question. Here's a tip for you. In every example or model that you're setting up, whether you're an experimentalist or a modeler, you will be dealing with either models that are represented by equations or a setup where you're injecting flow or particles or dye or something like that. There's always one or more degenerate cases where the solution is relatively simple. Okay? And those cases are typically the extreme cases, either as one parameter goes to infinity or if it goes to 0. Okay? So, and you would be lucky if you actually have a model equation for your system, because if your model equation that has no modeling errors, if it's truthful, it should reflect the physics correctly. So one situation here is when I look at this thermal conductivity. What should happen as K goes to infinity? That's an extreme case. So we're going to look at two cases, when K goes to 0 and when K goes to infinity. I said K is a parameter that the larger the K is, the faster, the better the heat transfer across the rod. So it's going to equilibrate really quickly, right? The heat is just going to be distributed really quickly, especially from that heating source. So what do you expect is going to happen as K is increased? Without looking at the equation, we're going to look at the equation next and make sense of that. Yeah?
There's almost no gradient between the different portions because they're transferring heat so quickly. So
no gradient? So this is still going to be at 500, and this is still going to be at, if they were both at 500, OK, I agree. Okay. But what if they're not both at the same temperature? So you're correct. If K goes to infinity and this is 500, or they're the same temperature.
It's a super rapid change.
What does that mean? Like, how can I catch that? Like, because this is super rapid, right? This is high slope, right?
Is it going to be linear?
Linear? Yeah. Like a straight line from 500 to whatever, 200 or 350. Let me adjust this a little bit here so we can make this more visible. Let's do it 200. Okay, why do you say that?
Because basically the resistance will be 0.
Okay, so hold on, let me put this at 400. I can make it look like this. Okay, who else has an idea? Almost the resistance is going to be 0 because you're not resisting that. So the minute the heat, we're not time dependent here. So it's wrong to say the instant that the heat comes in, but this is at steady state. But if K is so fast, then is so high, there's almost no resistance, like your colleague is saying. His hypothesis is that there's no resistance when this heat comes in. It's just going to spread really quickly. Okay. So what else? What do you think? I like this hypothesis, but you have other ideas. How about we play with it a little bit? Okay? We have a setup that gives us a solution. We kind of trust that solution a little bit, so we're going to try to see if it gives us the right answer, but also be careful. You might try it here, gives you the wrong answer, and then don't be stuck with that. So, okay, so let's go to 400. Kind of went down a little bit. Okay, went down a little bit, but there's still this peak. Let's go to 1,000. Oh. Okay, it's kind of coming down that peak. It's coming down. Let's go to 10,000. It's a straight line. Yes, good job. Let's go to 100,000. It's going to be the same. It's just a straight line. Just a straight line. That heat that came in didn't face any resistance. It just got balanced throughout the boundaries, just dissipated throughout. And you got a straight line. Okay. But how can you tell that this is correct? You're assuming that your code is giving you the true answer. In this case, it is, because I've verified this before. But suppose you don't know. You still have one more tool to help you reason about this. What is that? That's your model. Okay. So what happens if we go back? Let's look at our model and see what happens as k goes to infinity. If k goes to infinity, this becomes 0. So you have second derivative equal to 0. You integrate that once, you get a constant. Integrate it twice, you get a straight line. That's your exact solution. That's the beauty of these extreme cases. Okay, that's the beauty of these extreme cases. Here's a tip for you. Sometimes, sometimes you see these equations written k as k d2 k second derivative of t, k or kt double prime equal minus s. And then they tell you what happens when k goes to infinity. You'll be like, infinity times t double prime, there's no equation anymore. No, divide by k. Whenever you have a parameter that is not in the denominator and that's going to infinity, put it in the denominator and see what happens. The opposite is true. If you have a parameter that is in the denominator and that goes to 0, put it in the numerator and it's going to knock out everything, okay? Because it's going to 0. Okay. So now what's going to happen in the other case, in the other limit, when k approaches 0? So there's infinite resistance. The heat that you put in is going to keep heating that point indefinitely. Actually, this equation, so if you do what I just did, I multiply by k, you'll get this becomes 0, and this becomes sx equals 0. It doesn't make sense. The model breaks, actually, when k approaches 0. The model is going to break when k approaches 0. It's an inadequate model for very small thermal conductivities. And you can push this smaller and smaller, because we're still solving t double prime equal this. If you push k smaller and smaller, this is going to be infinity, right? So you're going to get something that's totally unphysical. So you can try it in the code, okay, but don't say, oh, my code gave me infinity. No, the answer here in this case is that the model is not correct anymore at those very small k values. So let's go to 1. Wow, darn it. You start at 500, you went to, you're making you're higher than the surface temperature of the sun here, 17,500, 19,000 Kelvin. That doesn't make sense, okay? It's unphysical, the material probably melted. You're not doing plasma dynamics here. The equation would be different in that case. So it's an unphysical situation. It doesn't make sense. And just by looking at the governing equation, you multiply by k in that case, you no longer have that second derivative. So there's no more of that balance. And then you get s of x equals 0, but s of x is not 0. The model is unphysical, okay? Okay, good. This was a good exercise. That's what I have for you with this large system of equations. You will solve a similar system in your homework assignment. And you can drive this, by the way, to more and more grid points. So you could put 1,000 over here or 10,000. And the solution with 100 points here is quite accurate. You don't need any more points. And you can manipulate the source term, whatever that is. The source term here is not entirely physical because it doesn't have, typically a physical source term here should have a switch where the temperature reaches a certain threshold, it switches off the source term so that you don't overheat the material. That's an example that you will do in your homework assignment where you're going to have a switch when the temperature reaches some environmental temperature called T infinity, then the source term becomes 0 automatically. There's no more source. Okay, so you'll do that in your homework assignment. I have a few points left to discuss with you. And I want to talk about matrix storage. Again, you might never hit this unless you're doing computational heat and mass transfer and fluid mechanics, that's going to be a big deal for you. For the most part, you are not going to deal with these sorts of issues, but I want to point those out. So I'm going to take the 2D and 3-dimensional version of what I just showed you. So this second derivative d2t by dx squared, in 2 dimensions it becomes the Laplacian, in 3 dimensions it becomes the Laplacian, the del squared operator. So you'll have partial second derivative with respect to t and x, a plus second derivative with respect to t and y, and so on. So you'll get something that looks like this. Del squared t or del squared u equals something or equal to 0. In 1D, it's this guy. In 2D, it's either combination of those two. In 3D, it's all of these things together. So what I'm doing here is I'm taking this Laplacian and I'm discretizing it. In 1D, it's a rod like we did. In 2D, it's a plate. In 3D, it's a cube or a rectangular prism, whatever you want to call it. And I put points in that, and I convert all of these derivatives like we did before, into these points, I plus 1 minus 2i plus t at I minus 1, etc. And same thing, you do it in all other directions. And I want to count how many terms there are in the system of equations that I'm solving. So later we will solve this in class together, in 2 dimensions. And the structure of the matrix is going to be similar to what we had before, except for 3 diagonals, you're going to have 5 or 7 non-zero diagonals, okay? And I want to count the entries. I want to get an idea of how much it costs in terms of memory to store these coefficient matrices in their dense form. So I'm storing the non-zero diagonals, and I'm storing all the zeros as well, okay? So in 1D, I have n grid points, n points. In 2D, I'm going to have n by n points. And in 3D, I'm going to have n by n by n. So 100 by 100 by 100, for example, or 20 by 20 by 20 points, or 10 by 10 points, or just 10 points. Okay. And now this would be the number of equations, right? So in 1D, I have n equations. In 2D, I would have n squared equations. And in 3D, I have n cubed equations. Because there's n cubed unknowns, I have n cubed points. The matrix size, remember, is number of equations times number of unknowns. So in 1D, just like we did in class, if I have n equations, then my matrix is n by n. In 2D, I have n squared equations, so my matrix is of size n squared by n squared. So if I had only 10 by 10 points in the grid, then my matrix is going to be 100 by 100. If I had 100 by 100 points, which is not much, you can see how that's going to explode. You're going to have 10,000 by 10,000. Okay. Matrix. In 3D, it's n cubed by n cubed, because I have n cubed equations and n cubed unknowns, so that's going to be the size of the matrix. So what I did here, I actually put this and put it in Python, and I asked Python, what is how much memory are you consuming to store these matrices before I even solve them, Okay, so for 3D, for the 3D case, which is the most realistic case, when n equals 16 points, so just 16 by 16 by 16, the matrix cost me 128 megabytes to store. 16 points is nothing. That's very low resolution. 32 points in each direction, that's reasonable resolution, took 8 gigabytes to store that. When I went to 64 grid points in each direction, and still that's nothing. Remember, the problem we did in class in 1D was 100 points, and 100 points was decent. So at least I would need, probably in the heat transfer case, at least I would need maybe 80 points or 75 points in each direction. But at 64, I capped at 512 gigabytes. So my computer ran out of memory immediately, and Python crashed. And I hadn't even solved the problem yet. Why? Because I'm storing everything. I'm storing the non-zero diagonals and all the zeros in the matrix, okay? And even the zero, when you store it in your computer, is going to occupy the same size as a non-zero entry in memory, right? It's a floating point, although it's 0. So the idea is that instead of storing all of the zeros, only store the non-zero entries along with the column and row that they belong to. So in other words, say I'm not going to store the zeros at all. I'm only going to store the non-zeros, and everything that I don't store, I know is going to be a 0, right? And so how do you do this? You essentially say, I'm going to store the non-zero, and I'm going to store the index of where it belongs in the matrix. Okay? So for each floating point, you're going to store 2 integers additionally to it. And then that changes your storage entirely. So for a dense matrix, where you're storing everything, these are the requirements. When you go to the storage method that I described, which we call sparse matrix storage, you go from, in 1D, you go from n squared entries times the floating point size to 3 times n. For 2D, you go to 5n squared, and for 3D, you go to 7n cubed instead of n cubed times n cubed. Okay, so practically, when you go to the 3D Laplacian, a 64 cubed grid cost me 14 megabytes instead of 512,000 megabytes. Okay, so you cut your storage by 3 orders of magnitude. We went from 512,000 megabytes approximately to 14 megabytes. Okay, so that's a lot. That's called sparse matrix storage. Can you do this in Python? Absolutely, and it looks almost identical to what we did right now, what we did with what we have right now. So instead of doing numpy.diag, you go to scipy and call scipy.sparse.diags. And you give it the diagonals. You tell it where it needs to put the diagonals. So the main diagonal is at k equals 0. The upper diagonal is at 1. The lower diagonal is at -1. And you store it like this. And then you can still solve this also with scipy.sparse.linearalgebra.spsolve. That's a sparse solver. Now, I'm not asking you to know this. I'm adding this for your own benefit, because next year or a couple of years from now, you're like, oh yeah, I remember Professor Saad talked about sparse systems. You know what? Let's do this. If we end up doing the 2D or 3D version of the Laplacian, we will use this approach. Okay. Anyway, I'm putting these for you here. These look the same, np.1s like we did before, and then you can just solve the system of equations, and it's going to give you the same answer. So what now? Well, you have everything you need. I just want to talk a little bit about the types of solvers, which we kind of did this kind of unconventionally, where typically people start with theory and then they show you results. I like to start with results and wins so you can see answers and then try to develop the theory with you. That's actually how we write our papers. The first section in our paper is results, because most people are going to look at the paper, okay, give me the answer, give me the formula, and then they want to dig in, they can dig in. So right now I want to dig in just a little bit into the types of solvers, and again, this is more like, these are not advanced topics. I mean, you are advanced, but these are not necessarily for almost everyone. These are become very specific for computational physics folks, okay? What I'm comparing here is so forget about this plot for a second. I want you to look at this plot. And here I'm solving the heat equation in 2 dimensions. So d2t by dx squared plus d2t by dy squared equal the same thing that we had, but now my source term is function of x and y. And I'm using a few different, so I'm storing this as a sparse matrix. It's a very large sparse matrix. And I'm using a few different solvers in Python. The first solver is this one in blue. That's the one we used numpy.linalgebra.solve. And on the x-axis, I'm putting the number of points in each direction. So obviously, as the number of points increases, you have a larger system of equations, and the cost to solve it is going to get larger and larger. Okay? On the y-axis, I'm showing the solver time, how many seconds it's going to take to solve that system of equations. So for example, for maybe 12 points, they're all kind of about the same here, for 15, 20. And once I hit about 32 points, I start getting to 1 second, and then 38 points, and then I think I capped at 40 points. And the cost of this blue one, the linalgebra.solve, was about 5 seconds. And you say, oh, Professor Saad, that's nothing. That's a lot. That's insane. 5 seconds per solve is insane. Why? Because you're not solving this once and going home. We are solving this over 1 million times in a full simulation of a fluid and heat and mass transfer and combustion. Because you're starting a fire and you want to see what happens to the fire in 2 hours. You're starting a tornado. You want to see what happens to the tornado in 2 hours. right? You're going to have to run it 1 second at a time or 1 minute at a time. And every time you're running that, you're solving a system like this. And multiply that by how many time steps times 5 seconds. It will take you about 5 years to run a single flame calculation, which is ridiculous. Okay? There are other things in the simulation that also take time. So this is a nightmare, unacceptable. However, you see here I have different solvers that perform better. This one in orange called conjugate gradient. It's a type of solver called iterative solver. You know, this one in black called SPSolve, that's the SciPy sparse solver. So that's a very special and fast solver for sparse matrices. It is the equivalent of this blue guy, but for sparse matrices. It's really fast. Look at that, it scales better. As I go to a large number of equations, it's still reasonable, but still when it hits 1 second here, that's bad. You know, and goes to 2 seconds, I don't like this. Then you look at this red one. This is a very advanced solver called algebraic multigrid iterative solver. That one almost stays flat. It scales really well. As you scale the number of equations, it stays flat. That's the kind of solver you want when you're doing some serious computing. Okay? So this is just to illustrate to you that there are different types of methods, different type of solvers. And I want to talk about this just a little bit. I know you've been hearing me talk about direct solvers. These solvers solve the system exactly, and that's why they're costly. But this solver, they don't solve it exactly. They solve it approximately. And that kind of solver is called an iterative solver. So here are the two general methods to solve AX equal B system of equations. What you know are direct methods like Gaussian elimination or LU decomposition. All these are exact solvers. They give you the exact solution for the system of equations. But be warned. You can't come and say, oh, I have the exact solution, so my solution is the truth. No, you have the exact solution to your model equations. What if your model equations are wrong? So if your model equations are wrong, you're solving the wrong equations very correctly. That is meaningless, right? So you should start with the modeling, make sure you have the correct equations first, and then solve them exactly or approximately. You know, I'd rather have correct equations that are solved approximately than wrong equations that are solved exactly. Okay? All right. So yeah, we've had that happen before. Like, yeah, I solved it exactly, but you got the wrong equation. But I solved it exactly. It must mean something. No, ink doesn't matter. Okay, iterative methods, they're much cheaper than direct methods, especially when you really don't care about getting the answer exactly, because there's so much modeling error everywhere. Why not just approximate the solution? So these types of methods are called iterative solvers, and specifically they are super effective for large sparse matrices. Okay, large sparse matrices. Okay, so the choice depends on the properties of this coefficient matrix, whether you're sparse or not. So I have a little guideline here. You start with your coefficient matrix. If it's small, then just use a direct solver and don't complain. If the coefficient matrix is large, if it's sparse, and I guarantee you it's going to be sparse in fluid mechanics, heat transfer, mass transfer, plasma physics, non-Newtonian fluid mechanics, all of these disciplines, the coefficient matrix is always going to be sparse. Okay? Going to be sparse. Then, if it's tridiagonal or pentadiagonal, which means only 1D or 2 dimensions, then you have a very special direct solver that is very fast, called the tridiagonal or pentadiagonal matrix algorithm. It's a direct solver, so you can get an exact solution at about the same cost of the other fast solvers. Okay? However, in general, when the matrix is sparse, just go to an iterative solver. The issue is when you have a large coefficient matrix that is dense. Okay, so that becomes problematic. Then you need special direct solvers, gradient descent methods, other methods. SPSolve actually is a special direct solver that fits here, actually, that fits over here. But that's kind of the general guideline for when you're dealing with linear systems of equations. So we're done with systems of equations. There's some additional material. If you are interested, I talk about iterative solvers and how we derive them, etc. Don't worry about that. Just up till here is good enough information. And again, to recap what I'm doing here, we're what, lecture 6 now. So, I'm trying to get you up to speed with the tools necessary to do some good, serious engineering. Okay, I know the course Foundations Engineering Analysis. I want to make sure that you all have the same tools that everyone else has in the class, so that once we get to more serious stuff next semester, once you get to more advanced stuff in mass transfer and kinetics that you can solve, you have the tools to solve those equations. I guarantee you that next semester, if Professor Sutherland says, okay, solve this system of equations, and you're like, I don't know, but you've seen it here, because I'm going to tell him exactly what I'm going to tell him, what you guys have been solving and what you guys are exposed to. So again, don't be too bored. I still need about 3 more lectures to get you up and running with all the tools that are necessary to do some good, serious engineering. So we still have nonlinear solvers, curve fitting, interpolation, and integration. So we'll cover those hopefully today and the next 2 lectures. And then we get started on some more advanced stuff.